In my earlier video, I had discussed about sequence of function. I had seen sequence of function is similar to sequence, but here each term be functions. So I had seen pointwise convergence of the sequence of function. Just recall again what is the pointwise convergence of sequence of function. The definition of pointwise convergence is, suppose fn is a sequence of function which is defined from capital A to R, then we say fn converges to f pointwise on the set capital A and limit n tends to infinity fn x equal to fx, or these fx be limit function. We all of us know, in my earlier video I had seen this part elaborately. This is true for all member of the x in the set capital A. Are you getting? Since here the limit function depends on the point, so this convergence is defined as a pointwise convergence. And in my earlier video, I had discussed many examples of pointwise convergence function. Mathematical expression will be, if for every epsilon greater than 0, there exists always be capital N such that small n greater than equal to capital N, the value of the fnx lies the epsilon neighborhood of the function a. Here f small f be the limit of the function. That means the sequence of function fnx for n greater than equal to capital N lies between the neighborhood of f function, that means f minus epsilon to f plus epsilon on the domain. This is actually the mathematical expression of pointwise convergence of a sequence of function. I will see this part also elaborately. Then I will define what is the uniform convergence in the sequence of function. I had said pointwise convergence function mean fx does not necessarily this preserve continuity or differentiability. Let's see one example at first about the pointwise convergence sequence. Just notice one example. Consider the sequence of function fn defined on the closed interval -1 to y by fnx equal to square root of nx square plus 1 over n, and this function is defined for each fixed x belongs to a. Here this is the sequence of function, and notice the picture. This sequence of picture would be such type. From picture it is easy to verify when the value of the function would be increased, then actually the sequence of function tends to mod x, and from this picture it is easy to say this sequence of function converts to actually the function mod x. Mathematical expression would be to find the fx, limit n tends to fnx who is equal to limit n tends to infinity nx square plus 1 over n. And from this expression we can write easily limit n tends to infinity x square plus 1 over n. And from this line, this is actually square root of x square, which is equal to absolute value of x. Means from this evaluation, we can tell fnx converges pointwise on the set A. Here A means my closed interval -1 to 1 on the function fx equal to modulus of x. And notice here fx not differentiable on A, because we all of us know absolute value of x is not differentiable at the point 0. Here notice, each term of the sequence of function obviously be differentiable. That means this sequence of function be differentiable, but it converges to f which does not differentiable at the point 0. Therefore, we can easily, in sequence of function, pointwise convergence does not necessarily preserve differentiability. Getting our next function is piecewise continuous function. Here domain is closed interval 0, 1 to r, fn defined from closed interval 0, 1 to r, and the function is look like fnx equal to n squared x times 1 minus nx, and this is defined in the interval x belongs to closed 0, 1 over n, and otherwise the value of the function be 0. At first, let's see the graph of the function. This is actually the parabola type, but at the point 1 over n, the value is 0. So the first f1 would be such type, and second f2 would be, notice the maximum value lies in this interval, and here the value would be fn 1 over 2n, 1 over n equal to n squared times 1 over 2n times 1 minus n times 1 over 2n, and this value is actually n over 4. When the value of n increase, then this value will be increased. Then the picture would be, next function would be such type. Here the peak would be increased, but this function is close to 0, and next function would be such type, and here notice, here the peak of the function will be in higher and 0 be larger. Okay, are you getting? And I hope you will understand that what would be the next function. Next function would be also such type function. What is the limit function is interesting. When x equal to 0, then obviously put the value, then fn 0 obviously equal to 0, and this is true for all n belongs to natural number. But when x greater than 0, then fnx would be 0, but here n greater than 1 over x. For this value, fn lies in the interval, then the value would be 0. On the other hand, when x lies here, then the value of the function will be 0. So we can tell easily the function is eventually 0. That means the limit of the function fnx would be, actually the function fx equal to 0. Okay, are you getting? Our next example is, this is also piecewise function. Here fnx equal to 0 in the interval minus infinity to 0, and nx in the interval 0 to 1 over n, and 1 when x greater than equal to 1 over n. And the picture of the function is look like, at first when n equal to 1, then f1x would be 0 when the interval lies minus infinity to 0, and x when this lies between 0 to 1, and when x greater than equal to 1, then the value of f1 would be 1. Notice, this is the f1 function. Similarly, this would be f2, and this would be f3, so on. Are you getting? Well, I will see what is the limit function fx of this function to To find limit of this function, here three cases will applicable. First, consider x less than equal to 0. Then obviously value of fx would be 0 for all natural number. That means when x less than equal to 0, then the value of fx would be 0 for all natural number. Now I will see for x greater than 0. For x strictly greater than 0, here two cases will applicable here. First, suppose x greater than equal to 1. That means here the point applicable here. So here also fx equal to 1 for all n. That means in the picture here fx x greater than 1 means just this line. Means here fx equal to 1 for all n. Now I will apply here in this interval when x less than 1. That means here applicable for this interval. That means when the point lies between 0 to 1, that means when the point lies between 0 to 1, then obviously we can apply Archimedean property. We all of us know this property. Then by Archimedean property, we can tell there exists k belongs to natural number such that 1 over x less than equal to k. Then for n greater than equal to k, we can tell 1 over x less than equal to k. Also, since n greater than equal to k, that means this is less than equal to n. That means obviously 1 over x less than equal to n. So that imply x greater than equal to 1 over n. Are you getting? OL. Means x greater than equal to 1 over n. That means the point lies here, and here the function fx converges to 1 for all n. That means actually fx equal to 1 for all n greater than equal to k. That means our limit function would be fx equal to 0 when x less than 0 and fx equal to 1 when x greater than 0. This is our actually limit function. Are you getting? OL. Here notice the sequence of function fnx here continuous, because here f1, f2, f3 so on are continuous, but the limit function does not be continuous. Are you getting? Why in the sequence limit in pointwise limit continuity does not preserve? Okay. Our next example is find the pointwise limit on the interval close 0 open infinity. The function is fnx equal to 1 if x greater than equal to 1 over n and nx if 0 less than equal to x less than equal to 1 over n. This question is similar to before question. Here has considered only positive interval. So see the picture. This is f1, this is f2, f3, so on. Now let's see what is the limit function of this sequence. At x equal to 0, since fn0 equal to 0, that imply fx converges to 0, and this is true for all n. Okay? And for x greater than 0, here two conditions will applicable. If x greater than equal to 1 over n, and other condition if x less than equal to 1 over n. At first consider x greater than equal to 1 over n. Consider x greater than equal to 1 over n. Notice when x greater than equal to 1 over n, then all fn x be constant function 1. So obviously fx would be at x equal to 0. Since fn 0 equal to 0, that imply fx converges to 0, and this is true for all n. Okay, and for x greater than 0, here two conditions will applicable. If x greater than equal to 1 over n, and other condition if x less than equal to 1 over n. At first consider x greater than equal to 1 over n. Consider x greater than equal to 1 over n. The picture would be, consider this is 0 1 interval, this is 1 over n, and consider x be here. And notice here interesting thing, at first consider this is x, 1 over n, as n tends to infinity goes to 0. That means 1 over n goes to 0, but still the point x is bigger than 1 over n. So obviously fx tends to 1 when x greater than equal to 1 over n. And this is true for all n. Are you getting? Well, our next condition is x less than equal to 1 over n. When x lies between 0 to 1 over n, consider x lies between here, and since 1 over n tends to 0 as n tends to infinity, that means 1 over n goes to this point. Consider 1 over n lies here. Okay? And here notice x is still bigger than 1 over n. So that means in the interval 0 less than equal to x less than equal to 1 over n, still fx converges to 1 for all n. Since when x greater than equal to 1 over n, the function fx tends to 1. Also when x lies between 0 to 1 over n, then also the function fx tends to 1 for all n. Therefore the limit fx equal to 1 when x greater than 0. Therefore the limit function would be fx equal to 1 when x greater than 0 and 0 when x equal to 0. Next example is the sequence fn defined by fn x equal to 0 when the interval lies closed 0 to open interval 1 over n, and otherwise fn x equal to sin pi over x if the x lies closed 1 over n to closed 1. This is the very interesting thing. The picture would be when n equal to 1, at the point 1, this would be sin pi, and we all of us know sin pi equal to 0. That means at the point 1 the value would be 0, and when I will consider 1 n equal to 2, that means on the interval 0 to half the value of fn x would be 0, and half to 1 the value of fn x would be sin pi over x. That means the picture would be, since the interval half to 1 the value would be sin pi over x. If we consider n equal to 3, then in the interval 0 to 1 over 3, the value of fnx equal to 0, and 1/3 to 1, the value of fnx equal to sine pi over x. Okay, then the picture would be such type, because 1/3 to 1, the value is sine pi over x. Okay, next this would be such type. Similarly, the picture said other point would be such type, then this, then this, then this will be continuing. And notice one thing, limit function would be fx equal to 0 only at the point 0, and otherwise the value would be sine pi over x. This is the graph. Okay, that means limit function fx equal to 0 when only x equal to 0, and when x greater than 0, then the value would be sine pi over x when x greater than 0. This is the limit function. Are you getting? Okay. By picture, it is obviously easy to verify why for all x greater than 0, why the limit function sine pi over x. Also, similar to before, you can apply here the Archimedean property. Then the result would be actually sine pi over x. Are you getting? Today I will stop here. In my next video, I will discuss uniform convergence of a sequence of functions. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel.